Internal Routing Protocols Part 1. Distance Vector Configuration with RIP version 2. Now, I already know what you're thinking. You're probably wondering, okay, two things. Number one, haven't they removed the distance vector routing protocols from the CCIE lab? And number two, isn't RIP a piece of cake? Well, let me answer both of those before we even get going with the objectives. Number one is no. That's a common misconception because they have removed the class full routing protocols from the CCIE lab exam. That is correct. And it's been confused and people think, oh, well, distance vector is gone. Not so. RIP version 2 is a classless distance vector routing protocol. It's one of the only internal protocols that is distance vector and classless. The second thing, RIP is easy. Also a quasi misnomer, and the reason I say that is because its base configuration is easy, but when you start trying to do things like they have you do on the CCIE lab exam, it can really get quite complex, and that's what I plan on doing in this nugget. Is first off defining why RIP. Why is it even still around at that point, and other RIP fundamentals. Then we'll spend about 2 seconds on the base RIP version 2 configuration and verification, and the rest of this nugget is all spent around this final bullet: advanced RIP redistribution, route filtering, and control. All the control of this protocol that we can afford it. But before we get into that advanced configuration, let's just talk about the facts to kind of get our blood flowing here. Number one, RIP is one of the oldest IP routing protocols that is out there. It essentially came out around the same time as IP itself, so that should tell you something about it. If it's been around that long, despite all of its limitations, it has to have some good, reliable, and simplistic setup methods. It was originally defined in RFC 1058, which is pretty old, and it was redefined as version 2, which added quite a few things in RFC 1721, 22, and 23. And this is what RIP version 2 adds to it. Number one, the long-awaited MD5 authentication. Before they had this, RIP was just begging for somebody to attack it by just opening a clear text sniffer and finding out the password and then injecting rogue routes and goofing up the routing table all around the network. It also added support for external route tags. So when you do a show IP route, you can tell, hey, that's a redistributed route into RIP. It's been received from some external network. The next thing it adds is multicast routing updates. So instead of broadcasting every 30 seconds to the whole subnet, it can multicast. And if you set up your network correctly, which I hope you have, you can then have it just go to the other RIP routers on the subnet. The switch, if configured correctly for multicast, can directly send those messages to only RIP routers. And the biggest one, and the best for last, is VLSM support. It is now a classless routing protocol, so you can change the subnet mask whenever and wherever you'd like. With those flyby facts about RIP out of the way, I'd like to take you straight into the configuration of RIP. And look at this. This is not your grandmother's topology that you're typically used to seeing for RIP. I mean, most of the time when you see RIP, it's in a Ethernet, a small Ethernet network with just a few routers running. That's where we're accustomed to it. But when you get to the CCIE, they'll have you using RIP in places you never expected. And this is an example of one. RIP version 2 is running across the frame relay cloud. Now, look up at the top. We have router 1. This is the hub of our network. It has DELCs to each one of the spokes, which do not have connectivity to each other. And this has been split. We're running RIP version 2 over on the left half of the network, which is tied together using a serial multi-point interface connecting to both router 2 and router 3. That's going to cause some troubles of its own as we see when we get into the configuration. Think split horizon. The second half of the network we see is running EIGRP, and it has a separate, router 1 has a separate sub-interface, 170.100.200.1, connecting on a point-to-point circuit down to router 4. Now we are going to be running RIP version 2, and I'd like to walk you through initially the foundation configuration of RIP on router 1. So let me go ahead and bring this up on the screen. And I'll get into global configuration mode on router 1 and type in router RIP. Now to include all of these networks, all I need to do is type in network 170, let me get that green box out of the way. It's a splinter in my mind. 170.100. And what class of network is that? It's class B. So .0.0, since RIP is a classful protocol by default. Now, let's look at something. This is one of the big verification commands that you'll use for RIP. Show IP protocols. We're running RIP, and what we see here down below is it's running on all interfaces since they all start with 170.100. And look at what's happening. Even though we're running RIP version 1, we haven't encoded it to run version 2 yet. It's sending version 1, and yet capable of receiving both version 1 and version 2 advertisements. We're going to be able to control that, and I'm going to show you that in just a moment. But before we do, let's convert this over. I'm going to get into global config, type in router RIP, and I'll type in version 2. That is it. Now let's look at the show IP protocol output after we've typed in version 2. This is big because if you ever see a scenario that says, hey, you want this to be compatible with both versions, do remember that as soon as you type in version 2, look at what's happened. We only send and only receive version 2. So if the other routers are still running RIP version 1, you haven't performed the conversion yet, what'd you just do? Well, you just cut them off. They're no longer going to communicate with each other. So that's a big deal. That's something to make sure you are aware of. So let's take a look at how we can change between versions on a per interface basis. The reason Cisco made this a per interface command is because who knows what neighbors you'll be connecting to. You might have one on Ethernet 0 in this example, or Ethernet, sorry, 1/0 is my little topology showing me here, that is running version 1. You might have one that's running version 2 on your serial interface. So you might need different versions for different interfaces. The way you set it up is by typing in IP RIP followed by send or receive. And the cool thing about this is the flexibility it gives you. Look at this. I can type in send followed by version. I can say version 1 or version 1 and 2 or just version 2 or just version 1. And I can do for receive, I can say for version 1. I can do any combination that I really want of those version numbers together. So I can send or receive any version that I'd like to. I can also convert this back to a broadcast-based protocol. You know, when we converted it to RIP version 2, it went to multicast. Well, maybe we don't want that. Maybe we want broadcast. Well, this allows us to convert it back to a broadcast base, although I'm not too sure why. We have authentication that we can perform on a per interface basis, and we'll get into that in just a moment. But let's jump back out of here. I'm going to keep the send and receive versions the same, just for consistency's sake. And I'm just going to do a show IP protocols one more time, verify that everything is running on this router. I have RIP. What I'm going to do is I'm going to pause the recording. And in the meanwhile, I'm going to go on all of the other routers. I'm going to set up router 1 for EIGRP over here and jump down to all these other routers and set them up appropriately for RIP and EIGRP where appropriate, so we have a full routing topology. Then we'll get into the advanced configuration and do some redistribution. Okay, I'm done. I've deployed RIP and EIGRP on all the appropriate routers across the topology. I'm going to do a show IP route on router 1. And what I have, as you can see down here, is some dynamic routes that are being learned of 170.100.4, .2, and .3, which if we look at our topology are behind here, .2, .3, and .4, and they've all been learned. I'm going to do a show IP protocols as well, just to show that we have RIP running, it's version 2 on this network, and it's routing for 170.100. Down below we have EIGRP running, and it's routing, sure enough, for 170.100, because you can see that all networks are kind of a Class B style, starting with 170.100, and right there is an instant bad practice that we haven't done yet. These protocols are running fully on every interface because every interface starts with 170.100. So this one, even though it's not supposed to be part of RIP, is sending out RIP updates. This one, even though it's not supposed to be EIGRP, is sending out EIGRP updates. So we need to change that. I'm going to get into router RIP config mode, and I'll type in a passive interface, And we'll do serial 0/0.2, which is the subinterface over on the EIGRP side. And it looks like the Ethernet interface is also needing to be passive, because that's also included in the EIGRP realm. So that keeps the RIP updates from being sent out those interfaces. Now on router EIGRP, I'm going to do the same thing, but with the serial 0/0.1 interface. So now I've kept the updates from being sent on the wrong interfaces. With that, we should be able to do a redistribution. I'm under EIGRP. Oh, holy cow. Jeez, that was almost detrimental. EIGRP 2000, I should have been under. And I'll just do a no router EIGRP 200. All right, now let me go back under router EIGRP 2000. And I'll do a redistribute RIP followed by the metric that I'm going to use. And this is the metric that the RIP routes will have as they come into the EIGRP domain. Now, some of you prefer to do the default metric command, and that's okay. I've done that plenty myself, but I don't know. Lately, I just prefer to use the metric under each redistribution command. So as I redistribute RIP and OSPF and everything into the appropriate protocols, I can just set the metric for each one. It's just become kind of my habit at this point. So I'll just go ahead and set the delay, the bandwidth, the reliability, the load, and 1500 is the MTU. You'll get in the habit many times. This is common metrics that a lot of people use just because it's very quick to remember and type. You'll probably end up being able to do it without context-sensitive help at some point. I'll also go under router RIP, and I'll do a redistribute EIGRP 2000, and we should be able to now just say the metric for this, we'll just say 2. It'll be 2 hops away for everything EIGRP that gets redistributed into the RIP world. So at this point, my thought is if I go down to, let's check the topology, down to router 2, we should see the routes over here in the Ethernet interface, and likewise on router 4 we should see all the RIP networks. Let's do that. Down on router 2, I'll do a show IP route. And let's see what we've got. I've got this one, R 170.100.200.0 with a 30-bit mask. By the way, instantly, just by looking at these 2 routes, I can tell that this is RIP version 2. You know how? Because it's accepting a variable length subnet mask. If this was RIP version 1, this route would not appear. It would not show up in the routing table, and that was actually one of the big dilemmas in some of the older CCIE labs, is you had to figure out how to make that show up even with a class full routing protocol. But this is classless because I am seeing all the routes, and I am going to, let me just verify the Ethernet network. Yep, Ethernet showing up as well. Let me hop on over to router 4 and do a show IP route. And it looks like on this side I'm seeing all the routes as well, and you can see them being marked as external routes. We have EIGRP being learned as external routes of the 2 RIP networks that are over on this side of things. So it looks like our redistribution is occurring successfully. But wait a second. You know, there's something I just thought of that this will make a great lab as we work through this. Take a look at the routing table one more time on router 4. Now, let me go back to the topology so we can see where it's at. Router 4, plugged into the EIGRP domain, right? Connected to 170.100.200, up to router 1. Connected to 170.100.4. These are all EIGRP routes, right? So, router 4 should only learn about this network up here, 170.100.10, via EIGRP. This should be learned as a redistributed route into EIGRP. I guess you could argue it is being learned by EIGRP, but it's an external route, right? Let's look at this again. 170.100.100.x. It's a 24-bit mask, so I'm looking, look at this top route right here. It looks as if EIGRP is learning it, but it's learning it as an internal route. It's not an external redistributed route, it's internal. Why? Well, because when we typed in network 170.100 on router 1, it included all of these in the EIGRP domain. And since EIGRP has a better administrative distance than RIP, it's saying, oh, well, I'm going to believe as if this were in EIGRP domain. Now, I just want to throw this out there right now for you because I'm going to come back to this once we get past a few more commands I want to show you. I want you to think, if your lab, your CCIE lab said that this route needs to be learned as an external route to EIGRP, how would you do it? How would you keep EIGRP from learning about this route as if it were an internal route to EIGRP? Think about that. We'll come back to that one in just a moment. Let me show you a few more commands that are just going to be awesome tools in your tool belt that you can use with RIP. The first one is, let's say we have this frame relay network, and RIP version 2 uses what? Multicast, right, to send its updates. Let's say your requirement said you can't use multicast or broadcast when you're sending across the frame relay cloud. Well, one of the things that you can do, let me jump back up to router 1 since we can see that one on the diagram behind us. Oh, I get my topology up there. One of the things that you can do is go into router RIP, and there is one command that you can use. It is just neighbor. Neighbor followed by the IP address of the neighbors you'd like to use. So if I were sitting on router 1, I would type in the IP address of router 3 and router 2. And what happens is as soon as I type in their IP address, just so you can see here, that's the only argument that there is, and it converts my messages to unicast. It will then unicast those neighbors rather than sending multicast to them. The other thing that you can use that is, this is going back to my kind of secret ninja commands, it's called an offset list. You ever hear of this one? An offset list. What you can do is you can apply an offset, and this thing has come in handy for me many times, to change the metric of specific routes. For example, let's say on router, well, let's change the routers. Let's say on router 2, I wanted to send this network up to router 1, but I didn't want that network to be sent down to router 3. And the requirements say you can't use a distribute list, or you can't use any type of route filtering per se, like a route map or anything like that. What do? I mean, what kind of strategy do you use? Well, here's the idea. I can create an offset list that specifies an access list. Let's say I created access list 1, and that access list permitted just this network, 170.100.2.0. I could apply an offset list, and I'd call on access list 1, and what I would do is on, let's say we're sitting on router 1, on incoming updates, I would set the offset of that network to 15. What's that do? Well, it adds 15 to whatever metric I receive. Well, actually, it'd probably be better to do 14. Here's what happens. Router 2 sends you this route, up to router 1. It receives it. What metric does it have? 1, right? Because it's 1 hop to get there. So we add 14 to that metric, so now router 1 sees it as a metric of 15. 15 is the biggest metric you can have for RIP before it's declared invalid at 16. So even though router 1 will pass that route down to router 3, what happens when router 3 gets it? You got it. It's filtered out. Even though you didn't use route filtering, you didn't use a distribute list, you didn't use a route map, you just set the metric to an unreachable metric by time it gets to that router. So remember that one, an offset lists. That's a handy command to have in your tool belt. One more for you, and that is the timers. You can change any of the timers on RIP to be more efficient, I guess you could say, because RIP sends updates every 30 seconds, and we could change it to be somewhere in the, what is that, 4,294,000,000 second range. You can increment it for anything between 0 and up to that huge amount of time between your updates. You do have to change that on all your routers, or else you're going to have chaos happening. But if you want to make your routing maybe a little more bandwidth efficient, I might say, well, I want to change it up to 60 seconds. You also have the invalid, how long until it's invalid. We'd say maybe 180 seconds, and then we have our hold down and flush timer that follows this that you get to specify. So you get to specify all of the different timers that you'd like to with RIP. You can dictate them using this timers basic command. But remember, anytime you set the timers, you are increasing your bandwidth efficiency. Anytime you set them longer like I just did, you do increase bandwidth efficiency, but at the same time you decrease, or I should say you increase your convergence time, how long it takes this network to converge anytime a fault is detected. But I want to come back to the gauntlet that I threw down back early on in this demonstration when I said router 4 is learning about this route over here via EIGRP as if it were an internal route. I could almost take this green boundary and include that network as well, because router 4 is learning about it as if it were an EIGRP internal route. Let's go back down there and just verify that one more time. Sure enough, there it is. 170.100.100 up there, .0/24 is being learned as an internal EIGRP route rather than an external one. And that's a pretty difficult challenge I threw out there because we're sitting on that local router. By typing in that network statement, we've included it. So here's what I want you to do. I want you to pause this video, this nugget, and think about it. Seriously, tax your own mind, run through some scenarios, and then come back and I'll explain a couple of the ideas that I have on how to fix it. Okay, hopefully you paused the recording and had a couple thoughts on it. And here's some of my thoughts. Looking at this topology, let me come back to the topology here. On router 1, in order to make this route look as if it were an external route, there's a few things that I could see being done. Number one, on router 1, we could adjust the administrative distance of either EIGRP or RIP. We would have to adjust it to where RIP is more believable than EIGRP. Because, as of right now, this one is winning because EIGRP has a better administrative distance. So I would say either go into EIGRP's routing process and adjust the administrative distance up to where it's greater than RIP, or come into RIP and adjust it down to where it's lower than EIGRP. You may have also thought about a distribute list, kind of filtering that route from being sent into EIGRP. That's a good thought. However, the problem is you'd filter the route completely if you used the distribute list, because it would filter it from being sent whether it's an EIGRP route or an EIGRP external route. So router 4 would stop hearing about that route regardless. Here's how I'm going to do it in this case, and I've got to admit this is kind of a cheesy way out, because this is a fairly new feature in the iOS, but it is a feature available in the iOS you'll be having on your IE lab. It is done from router EIGRP, and I'll go into 2000. It's the easy way out. I'm going to type in no network 170.100.0.0, and then I'm going to follow it up with network. You see my peer just went down. Network 170.100.10.0, followed by the wildcard bits. Yes, now EIGRP doesn't make you type in the full classful network. I can specify wildcard bits to where it's just like OSPF, and I can designate exactly what interfaces I would like it to run on. This eliminates the need for that passive network statement, because now I can say just run on this interface or just run on that one. And at this point, let's go down and verify on router 4. That route, voila, is now learned externally via EIGRP, because EIGRP is no longer running on this multi-point interface. Remember, even if we set up a passive interface, it's still running. But just for completeness sake, I do want to show you the distribute list command as well. It's available in any routing protocol that you can run, including RIP. If we ever wanted to go into RIP and filter some networks, for instance, maybe I didn't want this 170.100.10 network to reach these two routers down below. I didn't want router 2 and router 3 to hear about this Ethernet 1/0 network. Maybe it's a private network. What we can do is create an access list. And on, oh geez, I'm on the wrong router. Let me jump up to router 1, because that's where I'm going to do the filtering. I'll do an access list, and I'll just say 50. And what I'll do is I'll say deny the network 170.100.10.0 wildcard bits, and then access list 50, permit any. Then I can go under router 1, under the router RIP process, and type in distribute list, followed by the access list that's going to apply the filtering. I'll say 50 in this case. Then what direction I'd like to filter updates, and in this case I'm going to filter it as it's going out of this router, as it's leaving, so I'll say out, and then I'll say, I can even get more specific than that. I could say out serial 0/0.1, but in this case that's the only interface running RIP besides the Ethernet network. So I'll say when it's going out that interface, I want to apply distribute list 50, which essentially applies access list 50, which denies this network and permits anything else. So distribute list, By far one of the quickest, dirtiest, and easiest ways that you can use to filter out any network updates on the router that you specify inside of an access list. At this point, guys, that's really all there is to RIP. I'm trying to think of anything else I can add in there. I think that should be about it. We did the show IP protocols. Oh, a good debug. Let's do a debug IP RIP. This is the main command that you use anytime you're having troubles with RIP to see if you're receiving and sending updates at the specified intervals out on the network. And there we go. We have a RIP version 2 update that was received from this neighbor, 170.100.100.2, on this interface. These are the two networks that we heard about, and we see how many hops away they were. So we're able to see exactly what updates are being sent. We're also able to verify that this is indeed using multicast. You see it? Version 2 update to 224.0.0.9. That is the multicast address that RIP uses to send its updates out. If we were using broadcast, that would say to all 255s, 255, 255, 255, 255, because it would be a broadcast-based update. But that's really all there is to RIP. So in this nugget, we have seen pretty much everything that you can do with the RIP version 1 and version 2 protocol. We started off by talking about why RIP. Well, I guess I can't really answer the question of why. It's mainly just a network protocol for small businesses that have very few routers and just want routing to work. That's the beauty of RIP, is it just works. We then got into, I would say, about 1 minute of the base RIP version 2 configuration and verification, which is simple as typing in router RIP followed by the version number that you would like to run. You can then go under the interface configuration mode and you can specify what versions you'd like to send and to receive. The rest of the nugget was spent around the advanced configuration, setting up RIP redistribution, which we did between EIGRP, using route filtering, which could be done using a distribute list. You could apply a route map when you're doing redistribution, and we'll talk more about route maps when we get into pure redistribution chapters, especially when we talk about BGP. And then we talked about control, changing the timers, changing the administrative distance, doing various things to control your routing protocol, which is exactly what you need to get good at when you're getting into the CCIE lab, is knowing every tool that you have available to you in your tool belt. And I hope this nugget has been informative for you, and I'd like to thank you for viewing.